Okay, so this is the fourth question of JEE 2025 Advanced Paper 1. We are given a matrix P. This is a matrix, and the question asks how many matrices are there which satisfy these two conditions, that is Q inverse equals transpose of Q and Q commutes with P. QP equals PQ, that is Q commutes with PQ. Okay, so this condition actually means that Q of QT equals I. Okay, that is identity matrix. So we will see what it implies. Okay, I forgot to add one more condition. The third condition is that Q has integer entries. This one I forgot. Okay, so let's suppose Q has this form. This is the first row, second row, third row, and if Q has this form, then its transpose will be this. The first row becomes the first column, second row becomes the second column, third row becomes the third column. Okay. Now let's multiply them both. So Q times QT, the element at first row, first column will be obtained by multiplying a first element of first row with first element of first column, second element of first row with second element of second column, third element of first row with third element of first column. Okay, so I hope everyone knows how to multiply matrices. So this is simply A11 times A11, A12 times A12, A13 times A13, which is written in summation form as A1k times A1k summation k to 3, k equals 1 to 3. We can simplify it as A1k square. Okay, the second element of the first row is obtained by multiplying elements of first row with elements of second column. So it is A11 times A21 plus A12 times A22 plus A13 times A23. When written in summation form, it is A1k times A2k summation k equals 1 to 3. In the same way, the third element of the first row is A1k times A3k summation k equals 1 to 3. And the general element of this matrix Q times Qt, which we will denote by S. The element of the ith row and jth column will be obtained by multiplying elements of ith row of Q by elements of jth column of Qt, which will be Aik times Ajk summation k equals 1 to 3. So everyone please go through this and please keep all this in mind. I'm going to have to rub some of the material from here. Okay, we can still work without rubbing all of it. So let's take a geometric point of view. Assume that the elements of the first row represent components of a vector. So let's write vector A1 as A11, A12, A13. Similarly, vector AI will be written as AI1, AI2, AI3, where I equals 1, 2 and 3. Okay. So this is the vector A1. These three elements represent the components of the vector A1. This row represents the vector A2. This row represents the vector A3. Now the general element of this matrix X S. I will rub this. Sij equals summation k equals 1 to 3 aik aj k is equal to ai1 aj1 plus ai2 aj2 plus ai3 aj3, which is simply the dot product of these two vectors, ai dot aj. Okay, so we can write the matrix S as I am only writing the ith jth element at the ith row, element at the ith row and jth column. This is the ith jth element of the matrix S, and from here we get that this should equal the identity matrix. So ith jth element of the element at ith row and jth column of identity matrix is denoted as delta ij, which equals 1 if I equals j and 0 otherwise, which is simply we can see why this holds by writing out the identity matrix 0 1 1 0 1 0 0 0 1. Okay, so when the rows and column have the same number index, first row and first column it's 1, but first row second column is 0, first row third column it's 0. Only when column and row coincide the ith jth column is 1, otherwise it's 0. So this is a concise way of saying the same thing. So the gist of all this is doing all this exercise, we get ai dot aj equals delta ij. So when I equals j, we get ai dot ai equals mod of ai square equals 1. Let's write this out in terms of the components. We get ai1 square plus ai2 square plus ai3 square equals 1. All of these are real numbers, and if we take into account the third condition that Q has integer entries, then all of these are integers. So if we assume that these three numbers are integers, then there is only one possibility, that one of these three numbers is is equal to plus or minus 1 and the rest are 0. All of these can't be 0, otherwise this sum will be 0, and if any number, any of these three numbers is not 1 or minus 1, then this sum will be greater than 1. So the only possibility is that one of these three numbers will be 1. For example, A can be 1 0 0 or 0 1 0 or 0 0 1. The same holds for every other vector. It holds for all three vectors from A1 to A2 to A3. This applies to all three. Okay. Now we only used one condition. We assumed I equal to j to deduce this. I should write plus minus here. Okay. Now let's assume that I is not equal to j. I not equal to j implies ai dot aj equals 0. It means these two vectors are orthogonal, and it holds for any two pairs of ij when they are not equal. So summarizing all of this, we get that a1, a2, a3 are three mutually orthogonal vectors with mod 1. So, and because they have integer entries, we also deduced that their form should be what do I say? For example, plus minus 1 0 0. Okay, and it may be the second entry is plus or minus 1 or third entry is plus or minus 1, and the rest two entries will be 0. Now I am going to rub it. Please remember that these three vectors which we talked about are mutually orthogonal because it is going to be important. Now let's suppose A1 has A1 equals 1 0 0. Okay, or minus 1, plus or minus 1, anything. For the timing, let's suppose it's 1 0 0. 1 0 0. Now A2 also has plus or minus 1 in one of its entries, one of its column. But it cannot be that plus or minus 1 cannot be in this column. Okay, if suppose if A2 has 1 here, 1 0 0, then A1 dot A2 equals 1. Or if it was minus 1, then A1 dot A2 will equals 0. It will imply if A2 has non-zero entry in the first column, then it will imply that A1 dot A2 equals plus or minus 1. That is not equal to 0, which violates one of our condition that we derived earlier. So this column cannot have any more non-zero entries. It must be all zeros. This 0 we already fixed. Now suppose A2 has the 1 here, 1 or minus 1, whichever, then it cannot have any more non-zero entries. So this will be 0, and for A3 there is only one possibility left, 1. Or we may have we may have for A2 1 here, 0 here, then this column cannot have any more non-zero entries, so here we will get 0 and there is only one possibility left for A3, 1 or minus 1. I am only talking about non-zero entry, non-zero possibilities, okay. So this is how our matrix Q will be, okay. So this is actually a rearrangement of the columns of identity matrix. This is simply a rearrangement of the columns of identity matrix or rearrangement of the rows of identity matrix. If we ignore the sign, if we ignore the sign of the non-zero entries, then this is simply the rearrangement of the rows of this identity matrix. How? Exchange these two rows, we get this, and all other possibilities are obtained by permuting the rows among themselves. That is the only possibility, because the columns can only have one non-zero entry. So we have established this much. If we ignore the signs, then Q has the form obtained by permuting the rows of identity matrix. Now, how to deal with the signs? Suppose this is the form of Q. Q is this. Okay. 1 0 0 0 0 minus 1 0 1 0. Then we can write this as 1 0 0 0 minus 1 0 0 0 1 times 1 0 0 0 0 1 0 1 0. Okay, so we have factored out this sign as matrix multiplication here. Let's see that performing this multiplication we get this matrix. So we get 1 0 0 times this, we get 1. Then this row multiplied by this column, we get 0. This row multiplied by this column, we get 0. Now this row multiplied by this column, we get 0. This row multiplied by this column, we get 0. This row multiplied by this column, we get minus 1. Okay. When you perform matrix multiplication, you will get this. So for any possibility of sign, let's consider there are 8 possibilities for plus and minus 1 signs. First row may be positive, second row may be positive or negative, second row may be positive or negative, third row may be positive or negative. By a row being positive or negative, I mean the non-zero entry of that row being positive or negative. So there are 8 possibilities, 2 possibilities for each row, and 2 times 2 times 2 equals 8 possibilities for the whole matrix. Okay, so this is the condition. Now we have used 3 conditions, 2 conditions here. First this condition and this condition to obtain at this form. Okay. So let's write Q as a product of 2 matrices. One is sigma for sign, rho is for permuted rows. Rho is a permutation, matrix obtained by permutating the rows of identity matrix. Okay. For example, row equals 1 0 0 0 0 0 1 and 0 1 0, and sigma is obtained by adding plus or minus signs to the rows of the identity matrix. So one of the examples of sigma is 0 1 0 0 0 minus 1. So there are 8 possibilities for the sigma matrix, and there are how many possibilities are there? 6 possibilities for the row matrix, because 3 rows can be permutated in factorial 3 ways, that is 6. Now we have not utilized this condition till now, that QP should equal PQ. Now when we multiply Q with P, okay, when we multiply Q with P, we are multiplying with 2 matrices, rho sigma times P, okay, equals sigma times rho P. Rho is obtained by computing the rows of the identity matrix. The effect of multiplying rho before P is of permuting the rows of P matrix. So if you multiply rho and P here, for example, if rho equals 1 0 0 0 0 1 0 1 0, then multiplying it with P, two 0 0 0 2 0 0 0 3, it will commute these 2 rows, because we have you can observe it yourself. Okay, let's write the first row. 2 0 0 0 0 3 0 2 0. Here the effect is effect of multiplication of row on P is simply to permute these 2 rows. Okay, so if rho is obtained by permuting these 2 rows, its multiplication with P will have the effect of permuting these 2 rows. Okay, now let's multiply row in the other order. Let's multiply P and rho. P row equals 2 0 0 0 2 0 0 0 3. Okay, here the effect will be to permute these 2 columns. You can also observe that this matrix is obtained by permuting these 2 columns of the identity matrix. So here 2 2 0 0 0 0 2 0 0 0 0, sorry, 3 0. So these 2 columns got permuted. Okay, So what we actually mean by this? It means when multiplying Q and P, we permute the rows of P, and when multiply P and Q, we permute the columns of P. So and the sigma, this sign matrix, this commutes with all the matrices here. Here QP equals sigma rho P equals rho P sigma. Sigma is a sign matrix, and we can change the order of multiplication here. Its order does not matter here. Okay. So this actually says QP equals PQ, that is sigma rho P equals P sigma rho, that is sigma rho P equals P rho sigma. Sigma, the sign matrix is invertible. You can see that by calculating its determinant. Okay, its determinant is either 1 or -1, and when determinant is non-zero, the matrix is invertible. So since sigma is invertible, we can cancel it out. This effectively means that rho P should be equal to P rho, which means the matrix obtained by commuting the rows and matrix obtained by commuting the columns should be equal, should be the same. Now let's observe. If we commute this third row with any other row, okay, the 3 will change its row. But if we commute this column containing 3, if we commute any row containing 3, 3 will change its row, but it will not change its column. And when we commute any column containing 3, it will change its column, but it will not change its row. So the two matrices obtained by commuting rows and columns, which involve commuting rows and columns containing 3, can't be equal. So this must remain unchanged. So this fixes one thing for row. We cannot move row 3 out of its place. So this implies that the third row of the matrix of row matrix should be 1. This much is fixed. Okay. We fix the third row of the row matrix. Now let's commute these two rows. This row goes out of the question of the commutation. Let's focus on these two rows. Let's consider this matrix 0, 1, 1, 0, 0, 0. Multiplying it with P leads to changing these two rows. So we will get 0, 2, 2, 0, 0, 0, 3, 0, 0. Okay. And if we multiply P first, then it will lead to changing these two columns. We again get 0, 2, 0, 2, 0, 0, 0, 0, 3, the same matrix. Okay. So commuting these two rows gives the same matrix in any order. So row has only two possibilities, either 1 0 0 0 1 0 0 0 3 0 0 1 or 0 1 0 1 0 1 0 0 0 0 1. These are the only two possibilities left, because the third row is fixed and we can only commute these two rows of the identity matrix. So there are only two possibilities for the row matrix: 1 0 0 0 1 0 or 0 1 0 1 0 0. Okay. Now for the Q matrix, Q equals sigma times rho. Sigma equals plus minus sigma equals plus minus 1 0 0 0 plus minus 1 0 0 0 plus minus 1. So sigma has 8 possibilities. There are 8 possible sigma matrices and 2 possible row matrices, and their multiplication are all different matrices. So 8 sigma matrices and 2 row matrices give us 16 possibilities. So the answer is there are 16 possible Q matrices that satisfy these three conditions. Okay, that's it. We are going to close.